Okay, so we're in our Delta V cabinet in the boiler house control room. And what we're going to look at now is this yellow module here. That is our SIS module. It's a Delta V SLS 1508. If you look in the D2L and if you look under the lab, you'll see that I've got the manual in there for it. What's interesting about this module is, of course, it ties in with the Delta V system. It doesn't mean that your plant would have a Delta V DCS and a Delta V SIS system. We just happen to have that module here. A lot of the times what you'll see with an SIS system is redundancy. It's a school here, so we don't have redundancy. Normally we would have a minimum of two SLS modules for redundancy. And we would need that in order for us to maintain the integrity of our I/O, and we would want to do that with our SIS system. If you go back to when we talked about SIL levels, to meet the SIL, we would probably have to have redundancy here, just like we have voting systems, 2 out of 3 voting, for example, in order to meet that SIL level, right? So we'd be able to meet that probability of failure on demand. So the one nice thing about this SLS module is it's universal I/O. So you just wire into different terminals in here for discrete in, discrete out, and analog in, analog outs. Okay, so we've got them all marked here. So we've terminated our discretes and our analogs based on how we terminate in our and you can see in our terminations, and there's three different levels here. There's A, B, and C in here that we would go into. From there, and it's a little tight in there to wire it in, and that's normal though to have. It's the same thing here. If you look at any of our I/O cards here in our Delta V system, it's the same sort of scenario, and that's why we always like to take our wiring back down into a marshalling panel, so it's easy for the electricians in the field to pull their cables in without having to play around with I/O directly on the input cards or output cards. Anyway, so it's a universal module, different from the DCS where we have designated input cards, output cards, that sort of thing. And we wired down to a marshalling panel here, and you'll notice there's a bunch of relays here. Now, the reason that those relays are there is because the SLS module, what it does is it tests the integrity of the loop. And so every so often what it'll do is it'll just pulse an output. And what we found was that there was enough of current going through the loops that, for example, if we had a horn or a strobe in the field, sometimes the pulse would be picked up in the field and you'd see the strobe flash once, or you'd see the horn just beep. And so we had to put the relay in between. So when it does its testing to look at the integrity of the loop, there's not enough current to pull in the relay contact. So that's why we put the relays in here. So on the outputs, we actually have 6 relays, and that's the reason we put those relays in there. So from there, it's wired out to the field devices. So all the DOs would come through these relays and then go out to the devices in the field. 24 volts, of course, we need to bring our own power in. So we brought our own power in and we tie it in here so we can see our 24 volts. We have all our grounds are jumpered, and then so those would be our outputs coming from our SLS module, going to our relay, and that would go out to the field. So that's basically the design and the wiring of the hardware for the SLS 1508 SIS module Delta V. Okay, so we have filled out our bypass forms. They've all been signed off by operations. And now you can see on the screen that we have initiated all of our bypasses on our fire detectors, our ESD, our LEL detector, H2S detector, and our ammonia detector. So now we're good to go and do a calibration on our equipment without tripping anything or enunciating any horns and strobes. Okay, so now we're up looking at our fire and gas detection system that ties into the Delta V SIS. We have 3 strobes, blue, white, and red. The colors kind of don't match, but I'll run through them with you. Red is for LELs or combustibles. The white strobe is for fire detection. You would think it would be red, but it isn't, it's white. And blue is for toxic gas. So we have 3 different gas detectors here. This one here is an LEL detector. The one below it, GT02, this one is GT01. That's a H2S monitor, so that's toxic gas. And the other one here is ammonia, and that's GT4, and that one is toxic gas as well. The way that they sense the gas that's in the atmosphere is they're all electrochemical cells. So depending on how much usage you're getting with them, you might have to replace the cells every 1 to 2 years, depending on the plant you're in. Some plants are every 6 months. So those are the detectors. And then lastly, we have a horn. Now, this is addressable in a way that you can change the sound if you want. So we've got it set up for swooping or something right now. The other thing that we can do with some of the horns is we could have the one horn, depending on which type of gas enunciated our strobe, you could have the horn have a different sound. We didn't do that, we just set it up with one sort of swoop. So what's the other parts that we have up here? This is a field view DVC 6200, and this is a special SIS version. Now what this does is allow us to do partial strobe testing. So if we looked at this valve as, say, a fire isolation valve or a safety shutdown system, normal operation would be open. If you have a look at the indicator, you can see that the valve is open. There's also a solenoid on it as well, and that would be the trip device. What the field view SIS DVC lets us do is do a partial strobe test. So what we'll set it up to do, for example, would be to go from 100% open, say, to 80, 70% open. It would move in increments and then would come back. So you'd be able to make sure that you were going to get that valve off the seat. Now, I can tell you from experience, where we've had some of our fire isolation valves in the last plant I worked in, when we went and we shut down for an outage, the valve didn't close. Therefore, we had to go back and we had to go and close a manual valve in order to isolate the line. And what had happened was, where the ball was on the seat, it got all corroded, and we had material there, and it couldn't overcome that sticking force and close. Therefore, we lost our SIL, our safety instrumented level. So by implementing one of these SIS DVCs, we can go and test. Now we can set it up for a frequency, or we can just do it manually. Today we'll do one manually. The other things we have here is I have 2 fire eyes here. These are IR detectors. And right now they have caps on them. You take the cap off, that's just to keep them clean. And when we're testing, if you want to test one and not the other, we just take one cap off. So what these are doing is, this is going to simulate a pump that would have seals on it, and if the seals leaked, we could have an explosive atmosphere and we could get a fire. I've seen it in plants before where some pumps, the seals will leak and they'll actually have flames coming out of the seals. If we had that sort of condition, we would want to shut equipment down. So what we do with these is, we have it that if one of them picks up a flame, it'll enunciate the associated strobe, which is the white one, and the horn to let somebody know that there could be a fire in the plant. So the operations group would have to come up and do an investigation. If both of them picked up a flame, now you know there really is a fire. In other words, if only one picked it up, it could be for some sort of unknown reason. Maybe somebody had a permit and they had a welding rod or something close by, and one of them picked it up in the line of sight, but there actually wasn't a fire. And we wouldn't want to shut down our equipment on false alarms. So what we do is we have a voting system. So if both of the fire detectors, the IR detectors, will pick up a flame, bang, it'll shut down the pump, and it'll also close our fire isolation valve. And the last piece of equipment that we have here is an emergency stop. So if you go around and you look in your plant, you'll probably notice you have some pull stations. They're all different types. This one here, you can see it says pull to stop. The reason being is if I was to lean up against it, I wouldn't hit the stop button and shut everything down. When we test this, that will close the valve, shut down the pump motor, and it will also enunciate the horn, and all the strobes will go off. Now you might be asking, how come we have 3 different colors? Why not just one strobe? Well, if you're operations, you'd want to know what happened. So if I was an operator in the field and all of a sudden an alarm went off and I looked and I saw a blue strobe and the horn going, I would say, oh, okay, well, that's a toxic gas. So I better get out of the area, and I'll have to suit up and come out and then sniff the area, right? So the operations would want to know. So if it was an E-stop and you see all 3 flashing, you would know somebody hit an emergency stop. So that's the basics of what we have for our SIS system. This is our junction box here. So all the wires, all the cables came through this multi-conductor that was pulled into our SIS DCS cabinet down below. And then from here we go out with the individual pairs to all the devices. You see that I have some wires sitting in there and hanging there. The reason I did that was, and I'll open it up, and so if you wanted to do a calibration on one of the gas detectors, I can hook up a communicator here. And it's just easy to do it here instead of having to open up the cover. And we'll do a calibration, and then we'll do some tests on it, and we'll make sure that we check out the SIS system. One last thing about this is normally you would want to probably do the calibrations with a magnet, and that's what we'll do. And the reason being is if it's in a classified area, you don't want to open up a device that could be arcing and sparking. Therefore, it's probably better to use a magnet, and we'll do that. But if the junction box, for example, was in a non-classified area, by all means you can hook up here and use your communicator to do the calibration. It's the same thing. One last thing is these devices, they require a separate 24-volt power supply. So what we did was we mounted a couple of power supplies here. That's where these 3 devices are getting their power from, and we tied it in on a circuit with another power supply. So these are the 24 volts in here, and we take our 110 in here to these power supplies. Okay, so we're going to do a calibration on an ammonia detector. The reason I picked this one was it's something different you might not see in your plant. I mean, everyone's probably done an LEL or an H2S. We put the ammonia one in for the simple reason that not only are the instrument techs and technologists and technicians doing the calibrations here and doing this lab, but also the operators have jumped on board to do this lab. And if you remember 2-3 years ago now, there was an incident in Cranbrook or Castlegar, one of the two, and it was an arena, and two workers ended up being asphyxiated through ammonia gas through the chillers, and they knew that there was a leak in there. They went back in and worked. Pretty sad anyway, they lost their lives. So there's a big push to understand ammonia detection as well. And for the operators, they asked us to add this in, and I was more than happy to put it in there for them. So we got three different gas heads. So the mixture we have here is 50 ppm. So the device is set up for a 0 to 100 ppm calibration, 0 to span. And so you'll find that typically on these gas detectors, you always use a 50% of the span. So the LEL would be 0 to 50%, and also the H2S would be 0 to 50 ppm. Okay, so it's fairly straightforward on how to calibrate these. what we want to use is the magnet. So if you were in the field, like I say, if it was an explosive atmosphere, you'd want to use the magnet. So it brings up our menu, and we just have to keep scrolling down. And where it says where's our calibration there? Okay, so I've picked calibration, the concentration's 50, and it says execute. Successful, so now it's 0. Waiting for 0, so it's zeroing. Now you could use a 0 gas for this, but we don't have a toxic atmosphere here. The doors are wide open. There's nothing in here, so we're just going to assume that this is a 0 ppm atmosphere, and we don't have any ammonia in this plant either. So we're waiting for 0. So it's doing its 0. Okay, now we got to put the cal gas on. So we just put the head back on there. We'll open this up. And now it's doing its span on the cal gas. Okay, so the calibration is almost done. Remove cal gas, so we'll turn it off. Move the head. Now you can see it's going back to, should go back to 0. We shouldn't have any gas here. Okay, so it's slowly coming down to 0 ppm. Okay, so the 0 is finished. It's gone back to normal operation, and our calibration is complete. And now we'll finish our calibration sheet, and then we'll have to go down and we'll remove our bypasses. Okay, so we have completed the calibration of our LEL, H2S, and H3 detector, and we also tested the functionality of our fire detectors. So now what we're going to do is we are going to test the enunciation of the strobes, horns and strobes, and we'll follow along with our cause and effect matrix and make sure that we're enunciating the correct equipment. So just quickly, we'll go through the LEL detector. So the LEL detector is set to go at 20%. A pre-trip limit is 10. That would mean that if it got to 10, we would alarm on the screen, but we wouldn't have the horns and strobes enunciating in the field. The same with the H2S. It's at 20 ppm. The pre-trip would be 10. It would come into the operator screen. And the NH3, the pre-trip is 25, and the trip limit is 35. All of these are taken from, the limits are taken from OH&S and also from WorkSafe BC. So if you want to have a look it up, you can find out what the limits are there, and we've gone through this, I think, when we did the lectures. So now it's time to go ahead and do the function testing. Okay, if you're following along with your cause and effect or shutdown key, what we're going to do is we're going to bump test our combustibles analyzer. So I've got the 50% LEL mixture here, and so I'm going to turn this on, and we should have the red strobe and the horn should enunciate. our trip was at 20%. We're way below. These have latched now. The reason we have them latch is because we want operations to come to the field and find out why this has gone off. Even if this comes back to normal, we still want to clear the area. All permits would be void, and we need to go and sniff the area and find out where this leak was, or if there was a leak. Okay, so you can see that our gas detector has come back to normal. Our LEL is here. But you can see that we've latched here. Our red strobe is still enunciated, and so is our horn. So I gotta hit the reset. Confirm. Okay, and the same with the horn. You can maybe still hear it. Reset. Confirm. And later we'll go into Control Studio and we'll have a look at the configuration as well on the inputs. Okay, so now we're going to check out our toxic gas for H2S. So for H2S, the blue strobe should come on and the horn should come on. So we'll do our bump test on it. And this is a mixture of 25 ppm. We just use this for bump testing. No, we don't calibrate with this one. We use the 50 ppm for that. Low alarm right now, which is on the screen. So that'll be on the operator station once we hit 20. So by this time, if you had a gas badge on you and you were smelling anything like that, you probably have your gas badge going off. Picked anything up. There we go. Tight enough. So there's our blue strobe and the horn. So now I'll take the gas off. Again, it will have latched. So we're below our trip point now. We're in just our low alarm. That rotten egg smell in the air right now, a little bit. And I'm going to go down and reset. Okay, so now we're going to function test our ammonia. Again, follow along with the cause and effect shutdown key. So we'll gas our ammonia. Okay. And then we should have the horn and the blue strobe. So this one goes at 35. Our low alarm's just pulled in. And at 35 ppm. Okay, so now we need to test our fire detectors, make sure the white strobe and the horn come on. Again, it's a voting system, so if we have one of them ring in, the strobe and the horn will come on. If both of them ring in, then the strobe and the horn will be on, but it'll also shut down our isolation valve that's simulating a feed to the pump, and then the pump will shut down as well. So right now I've got the cover on one of them, and I've got a little B-tank here, benzomatic propane, so I'm going to go and put a flame in front and simulate if we had a flame coming out of a seal on a pump. Done it with a magnet as well, but I prefer to use a real flame. So I'll go and reset, we'll check the other one, and then we'll get both of them to ring in, and we'll watch the valve will shut, and the motor will trip on the pump. You'll be able to see it in the DCS. Okay, so now we're going to test the other IR scanner. So I've got the cover on GT3B, this is GT3A, and we'll see if we get our horn and strobe. So we've enunciated our horn and strobe, and we know that the 1 out of 2 voting works for the horn and strobe. Let's see what happens now when we have both of them pull in. Now we should get the 2 out of 2 voting, so this is going to tell us we have a real fire. Now let's say this was a charge pump, maybe for a fractionator tower. That was the feed coming in through our valve here. We want to stop the feed coming in because we've got a fire happening on the seals of the pump. 2 out of 2 voting. Now you can see the valve shut. That's part of the safety system. And if we were to check downstairs the motor, you would see the motor has stopped in the MCC. There's a contact in there, and we can go down and have a look at that. There's a contact in the motor circuit that comes from the SIS system. That needs to be closed in order to energize our start-stop on our motor. So as soon as we had the 2 out of 2 voting, we tripped, that contact opened up in the starter, and we shut down the pump as well. Okay, so you can see on the screen now, we need to reset our strobe and our horn. Also, we need to reset our solenoid valve for our on-off valve, HY01. And also, we need a pump reset in order for us to start the motor again. So we'll reset the strobe first and confirm the horn. There, it just went silent. And we'll confirm the valve. And our valve just opened up again. And there's our reset on our motor. It doesn't automatically start. We have to go in and open up our faceplate, and we have to acknowledge that it has failed. Acknowledge. There we go. And we need to hit our stop button. That's the way the logic is on the stop-start station. And then we can start it again. And there we go, the pump is starting. So what I'll do is I'll stop that pump, and we'll have a look at that contact that's in the starter. There's a relay in there, and we energize that relay from the SIS, and then it closes the contact on the starter circuit. I'll go through the starter circuit with you. Okay, so our pump that is upstairs, and just so you know, we actually haven't pulled the cable to the pump yet. We've got to get the electricians to do that for us. But we're simulating the start-stop here. We just don't have the T-leads connected for that cable. So if we were to go and have a look inside this starter, I'll show you where the relay is, and that would be where we're using the contact right here. So you see our relay here. So right now that relay is energized. There's a contact in there that's in the starter circuit. These are typical. So here's our control relay here, and there's the contact that is in the circuit for your start-stop. So what happens when the SIS trips is it de-energizes this control relay, and then that opens up, and then we trip the pump. Okay, so the last thing we need to check off on our function testing is our pull station, our emergency stop. And so what should happen was when I pull this, if you look at the logic on the cause and effect, or the shutdown key, this valve should now close. The motor will shut down. All three strobes will come on, and the horn will enunciate. And I know that in your plant you'll have noticed that you have probably some ESDs. Some of them have cover plates on them. The ones that we had on site were similar to this. They had a cover plate, and once it was pulled, actually it had a key, so you couldn't reset it. You had to have a key to reset it. Operations had the keys. Depending on the type, some are push, some are pull. Normally if they're push, they will definitely have some sort of cover on it, so that you don't get a guy with a scalpel pole shutting down your plant, right? Some of the other ESDs, believe it or not, they won't only shut down equipment. Some of them, depending where they're at, are tied to a deluge system. So if you hit an ESD, sometimes you might get a little wet as well. So I know that you've always wanted to hit an emergency stop. I know everybody's wanted to do it. And if you were here live, we'd have to draw straws because everybody wants to pull the stop button. But I will do it. You can live vicariously through me for the day, and I'm going to pull the button. Our valve is closed. We've shut off our pump, and we have all three strobes and our horn enunciator. Now we have to reset. Okay, so the last thing we're going to test on our SIS system is we're going to do the partial stroke test on our DVC 6200 SIS. So what we want to do with this positioner is we want to go online, and then we want to go down to configure. You can see it's the DVC 6200 SIS, and we'll go down to calibration, and we'll go down to PST, partial stroke test cal. Okay, cal will cause sudden changes. Okay, so we want to enter that. Yeah, continue. Now we have the partial stroke test of where it's going to stroke it to configured already. Giving our supply pressure. And it's not a fast process, it's tedious. You could probably go and have a coffee and come back. Okay, so enter desired stroke test speed. Well, let's go to 1% per second. Down here if you want. Starting point, you should be able to see the valve move. Target is a 99.9% travel. Okay. moving at 1% per second, and the target is 70% travel. Yep. Travel's moving. Target speed 1% per second. So 30 seconds to get to 70%. Now it's collecting data and it's a little slow. So the travel is moving back to 100. Right now it's at 96. Now it's gone back to 100. So now it's collecting the data. Okay, so now the partial stroke test is completed, so we say okay. And we want to put it back in service. And by the way, even though it was out of service, the solenoid that's on here would override everything and shut this down if we had a trip. It's back in service. So it doesn't matter what the DVC does, it's always overridden by the solenoid. And that's tied into the SIS, okay? And so we're done now. Let's come out, calibration, and you can go into setup, for example, and you could have a look where you want to set up your travel, your tuning, everything else. So that's already been done previously, and you guys, depending on what you want to do in your plant, how fast you want the actuator to stroke, you can set all that up. The overview, pressures, analog input, travel, information, etc. Okay, so that is pretty much it for our SIS lab and gas detection. As you might have noticed, we actually run real process in here, and we tried to set this lab up so that we wouldn't shut down any real process, so it's all simulation. But that is a real gas detection system. That is a real fire detection system. It might not be anything hooked up to the pump or to the valve, but everything else here is what you would actually see in a plant. So I hope you learned something from this. If you have any questions, you know I'm here for you. Ask away. Bye for now.